Raising something to the power is just multiplication. Okay? So it follows the multiplication rules. So if you've got something that's got 3 sig figs and you're squaring it, your answer should have 3 sig figs. Okay, so it's just multiplication. Raising to a power is just multiplication. If you've got 3 multiplications and then a division, those all follow the same rule, fewest sig figs. So you could round once at the very end. Type all the multiplication division, get an answer on your calculator, round at the end. If it's all addition and subtraction, line them up, do the adding and subtracting, and only round at the very end based on what your numbers were you started with. Okay? So if there's multiple steps, as long as they're following the same rules, all addition and subtraction, or all multiplication and division, then you can just follow those rules once. We want to round as little as possible. But what if I have addition and multiplication in the same problem? What do I do then? Well, first of all, you do it in the right order. Just like in math class, parentheses, exponents, multiplication, division, addition, subtraction. Okay, so you have to follow the rules. But these rules from here to here are all about sig figs, and from here to here it's about decimal points, decimal places. So when I make that switch from multiplying and dividing to adding and subtracting, when I change rules, when I change sig fig rules, I need to stop and round off. Because if one tells me to round to the second decimal place and the other one tells me to round to 3 sig figs and they disagree with each other, which one do I follow? Well, the answer is you follow the right one when you're done doing that math. So you do the first one, you round off, then you do the next set of operations until the sig fig rules change, and then you round again. Or you round when you're done. So let's try a couple of those. $273.25? Yes. Can you hear me?
I'm not seeing anything. Are you supposed to be showing us something?
Okay. Can't. My share didn't work. Too many buttons to click. I'll get it here in a second. I can just get Zoom to work for me. Strange. Let me know when that happens, because this doesn't always. There we go. Okay, so if I want to do this problem, 273.25 grams divided by 75 milliliters minus 9.2 milliliters. Okay, I recognize that this is subtraction and that's division. So subtraction means decimal points, division means sig figs. So I got 2 separate rules. So according to, please excuse my dear Aunt Sally, I have to do parentheses first. And in the parentheses is a subtraction. So 75.1 milliliters minus 9.2 milliliters. That's 11, makes that 9, that's a 14, that's a 5. I get 65.9 milliliters. Okay. Now worry about sig figs. Last sig fig, last sig fig. They're both one in the tenths place, so that's why I round. So my denominator is now 65.9 milliliters. Then I do the division. 273.25 divided by that. It's me 4.146 433,991. Whew, I forgot the grams up here. So, where do I round that off? Well, now it's division. This has 5 sig figs. That has 3. The smallest number is 3. So it should be 4.15. And the units had grams on top and milliliters on the bottom. So it should be grams over milliliters. Okay. So I rounded when I did subtraction, and then I rounded when I did multiplication. Let's try something as simple as this. 2.5 times 1.8 plus 3.3 times 2.7. Okay. We're going to do the multiplication first. So 2.5 times 1.8 equals, on my calculator, that's 4.5. This has 2 sig figs. That has 2 sig figs, so my answer should have 2 sig figs, and it does. 3.3 times 2.7. Calculator says 8.91. Okay. 8.91. But this has 2 sig figs, that has 2 sig figs. So I need to round that to 8.9. And 4.5 plus 8.9. I get 13.4. Is that right there? 12? Yeah, 13.4. Okay. Well, what about sig figs? Well, now I'm adding. So one sig, tenths place, so I round it off in the tenths place. So my answer is 13.4. Notice that 13.4 has more sig figs than any of the numbers you started with. Because you had an addition in the middle of it. Adding can change the number of sig figs. Subtracting can change the number of sig figs. If you're adding, you can get more sig figs than you started with. If you're subtracting, you can end up with fewer sig figs than you started with. So adding and subtracting can change the number of sig figs. Okay. So here we have a math problem where we got something with 3 sig figs, something with 2, something with 4, and something with 3. How many sig figs are supposed to be my answer? Well, you can't really tell because there's a subtraction in the middle of it. Actually, not in the middle, at the beginning of it. So 9.23 minus 8.4. I get 0.83. What about sig figs? It rounds off there. So my numerator is now 0.8, just 1 sig fig over 1.882 times 453. And that's all just multiplication division, so I can just push those buttons. 0.8 divided by 1.882 times 453 And my calculator gives me 192.5611052. Think about sig figs. 3 sig figs. 4 sig figs. 1 sig fig. Smallest number is 1, so I got to round this to 1. That's the 1. Behind that 1, there's a 9, so I make it a 2. But 2 is nowhere close to 192. To keep it the same size, I have to put the 2 placeholders in. Because 200 is close to 192. 200 is 192 with 1 sig fig. It's okay? Right? So it's not any new rules, just a matter of you got to stop and round along the way if you're going to change rules. Okay. Now I want to tie a couple of pieces together. We talked about scientific notation. Now we're going to talk about scientific notation and sig figs. What does scientific notation do to sig figs? Well, actually, it's your friend. Okay. First of all non-zeros are sig figs. Okay. But that's true not just in scientific notation, it's all the time. Okay. But remember, in scientific notation, you start with a number between 1 and 10 times 10 to some power. Right? You got some number times 10 to some power. Now, if you've got a number between 1 and 10, it's going to be something, dot, and then all the other numbers after it. And you cannot, any zero you put after the decimal point is either going to be in the middle or is it going to be at the end. So ending zeros will be after the decimal point where they count. Like in 1.20 times 10 to the third. Or if I'd had 1.02 times 10 to the third. There's the only places that zeros can show up in scientific notation. They can show up at the end, where they count, or they can show up in the middle, where they count. So in scientific notation, as long as you got that number between 1 and 10, zeros automatically count. So everything you write down is a sig fig. Sometimes you have to write it in scientific notation to get the correct sig figs. Let's add 29,516, and I want to round that to 3 significant figures. No, sorry, 2 significant figures. Sorry, I guessed badly. 2 significant figures. I want to round that to 2 significant figures. Well, the first one's the 2, the second one's the 9. Behind the 9 there's a 5, so I'm going to put a 0 there, and I have to put all the placeholders in there. Because 30,000 is really close to 29,516. But 30,000 only has 1 sig fig. I need to make that 0 count. The only way that 0 would count is if I wrote 3.0. That would make that 0 count. But 3.0 is not the same size as 30,000. So now I do the scientific notation part. Okay, times 10 to what power? Well, I moved the decimal point 1, 2, 3, 4 times. And I made the number smaller, so I need to make the exponent bigger. So 3.0 times 10 to the 4th. That's 30,000 with 2 sig figs. Notice the 0 goes after the decimal point where it counts. And that's where it's got to go every time. It's got to go after the decimal point because you can't start with a 0. Because if you start at 0.15, you wouldn't be between 1 and 10. So the 0 will never be in front. So zeros will always count in scientific notation. Okay. Okay. So when you're multiplying and dividing with scientific notation, the times 10 doesn't do anything to the sig figs. It's just the numbers in front. And the same rule is the fewest sig figs. So if you look at the numbers in front, or sorry, you look at the numbers in front, the 1 to 10 parts. All you have to do is multiply those 1 to 10 parts and round to the right sig figs there, and then fix the exponent. In addition to subtraction, that doesn't work because you have to line them up, and they're not really lined up until they have the same exponent. Remember, scientific notation moves the decimal point around. So if you don't have the same exponent, your decimal point's in a different spot. In my last example, the decimal point was between the thousands and the 10,000. Okay? So scientific notation, you're moving around your decimal points, so they're not really lined up. Okay? Then you do the lining up and furthest to the left. Okay. Oops. So let's try a couple. It was right here. Where'd they go? Okay. So, first thing you're going to have to get used to doing is noticing that this is not three multiplication problems. This is two numbers. This is a number. This is a number. All we're doing is multiplying two numbers together. And think about how you did this in math class. First, you multiply the numbers in front. 6 times 3.8. My calculator gives me 22.8. And then, dealing with the exponent part, okay, this got an exponent of 3, this got an exponent of 2, and I'm multiplying, and when you multiply, you add exponents. So I get 22.8 times 10 to the 5th. Because 3 plus 2 is 5. But this is not between 1 and 10. So to get it between 1 and 10, I got to make it 2.28. That means I need to change the exponent. I made the number smaller by 1, so I need to make the exponent bigger by 1. And I get 2.28 times 10 to the 6th. Now I can think about sig figs. That had 2 sig figs. That had 2 sig figs. So my answer should have 2 sig figs. The second sig fig's the 2, so I get 2.3 times 10 to the 6th. Okay. It's not different math. Okay? It's math like you always did. 6.0 times 10 to the 3rd is 6,000. Move it over 3 times. 3.8 times 10 to the 2nd is 380. You multiply those on your calculator, it's going to give you 2,280,000. Okay? It's going to give 2,280,000. Here's why you don't want to do it this way. Because if you look at this, you're going to say 2 sig figs, and that looks like 1 sig fig. But it's not, because it came from there where it had 2. You can't lose a sig fig when you translate, so that 0 really counts. So I got 2 sig figs and 2 sig figs, so I get second sig fig. Turn the 2 into a 3, put in all my placeholders, and I get 2,300,000, which is 2.3 times 10 to the 6th. We don't have to do all that work every time. We just need to do this piece. I just wanted to show you that it wasn't different math than you've been doing before. You're just doing it with a different form of the number. Reasonable? Okay, so division would work the same way. Do the division of the front, subtract the exponents. Now I got these numbers, and I want to subtract them. I cannot subtract these two numbers because they have different exponents. So I'm going to take 6.08 times 10 to the third, and I'm subtract 3.2 times 10 to the second. That's my goal. But I really need to line them up, and these exponents aren't the same. So I need to fix one of them. It doesn't matter which one, but I find I have more luck if I make the small one bigger. So the small one's the 2. I'm going to change that into a 3. Now, since I changed that into a 3, I made the exponent 1 bigger, so I need to make the number smaller by moving the decimal point, and that gets me 0.32. So if I take 6.08 minus 0.32, I get 5.76 times 10, and I keep the exponent. It's just telling me what I'm adding, so they're at the same. Those decimal places are the same. I'm subtracting, so those decimal places are the same. So I keep that exponent when I'm adding and subtracting. Then I think about sig figs. A 0 there, a 2 there. So I get a line here. Whoa, it is the 5.76 times 10 to the third. That actually is the right answer. Because what you really did was you took 6,080 and you subtracted 320. And you got 5,760. The 8's a sig fig, the 2's a sig fig. So I round off there, I get my 5,760, and then I put it in scientific notation, and I get that. Adding and subtracting is harder because you always have to check those exponents. You always have to make them the same. So remember I taught you adding and subtracting first because it was the harder of the two. Okay? You got to line them up. Okay? So these are not the same numbers because they got different exponents. Now I got negative exponents. What do I do with negative exponents? And it's addition, not subtraction. So I got to do this 6.08 times 10 to the negative second plus 3.2 times 10 to the negative third. Now, I can't add these numbers because the exponents aren't the same. So I usually make the small one bigger, and negative 3 is smaller than negative 2. So I'm going to cross that out and turn it into a negative 2. I've made my exponent bigger, so I got to make my number smaller, so that needs to be 0.32. Now I can add them. My calculator is going to give me 6.4 times 10 to the negative second. But think about sigfigs. That's an 8, that 8, and that 2 are both sigfigs. Those are both 2 decimal places. I need 2 decimal places here. But I only got 1. What's missing? The 0. I need that 0 to have something in the second decimal place. I have to write it in. Because what you did was you added 0.0608 plus 0.0032. You got 0.0640. Still have to keep that 0. No matter which way you do it, you got to keep that 0. Because that 0 is your last sig fig. Say, well, Mr. Green, I don't understand what scientific notation. Let me just do all the math outside of scientific notation. I don't want to do that. Well, would you want to write this one out longhand? 5.33 times 10 to the 23rd. Do you feel like writing 21 zeros after that 3? And then lining it up with subtraction. Then lining it up with the 3.8 and changing that exponent. Ooh. You're only going to have 20 zeros after the 8. They're not the same exponent. You can't do the math until they are. 5.33 minus 3.8. Oh, can't do that. 5.33 times 10 to the 23rd minus 3.8 times 10 to the 21st. Okay, not the same exponent. I'm going to make the small one bigger. 22. No, I don't want 22. I want to go all the way up to 23. I want them to be the same. I want this to be 10 to the 23rd. I made this 2 bigger, so I need to make this 2 smaller. 1, 2. So that's 0.038. Move it over twice. So I'm going to do that. Okay, do that subtraction. 2, 9. Nope, I subtracted badly. So I get 5.292. $298, sorry. No, 292. I had okay, 5.292. Now sig figs, 2 decimal places, 3 decimal places. So I cut it off there. And you get 5.29 times 10 to the 23rd. Okay. So I got 3 sig figs, even though that only had 2 sig figs. Because it doesn't matter how many sig figs they have when you're adding, subtracting. It's where the decimal places line up. Okay. So that's how you do the math longhand. But many of you have difficulty doing it without a calculator. So we'll talk about how to use your calculator to do scientific notation. If you got a calculator, that scientific calculator, I'll talk about what that looks like in just a second. And I'll talk about how to get scientific notation into your calculator. Okay, so what makes something a scientific calculator? It has one of these 3 buttons. A button that says EE, a button that says EXP, or a button that says times 10 to the X. It's got to have one of those three buttons. Okay? Because what that button's going to allow us to do is to get those really big and really small numbers in there. So whatever that button is on your calculator, it stands for times 10 to the x. It's got the 10, it's got the x, it's got all of that built in. For example, this is Windows Scientific Calculator, the one built in. And the button we want is the one that says EXP right here. So 2.3, I hit the EXP, and it writes an E with a, and then I put in a 5. Okay, that is how this calculator is going to write 2.3 times 10 to the 5th. So all built into that E is times 10 to the. And that is, ooh, oh, it's multiplying. What the heck is it doing? Okay. So notice that this is a problem. There's a 10 to the x over here, but it doesn't do what I expect it to do. So 2.3 EE5 equals 2.3, 5.3 EXP negative 3, and I get 0.053. Okay, calculator wise, okay. Calculator wise, here's where they are on other calculators. I can just, okay, there's my lovely face. So this is a Texas Instrument calculator. Okay, and let's try to zoom in. On Texas Instruments calculators, the button is usually right above the 7. So right above a 7 on this calculator is a button that says EE. It does exactly the same thing as the EXP button does on the on-screen calculator. So Texas Instruments have it above the 7. There's one over here that says 10 to the x. We don't want to use that 10 to the x, not until we learn what it does. But this EE stands for times 10 to the. It's got the times, it's got the 10, and it's got the exponent all built into it. On Casios and Sharps, they actually have, Casios, they actually have a button at the very bottom that says times 10 to the x. So that when you push it in the calculator, you type 2.3 times 10 to the, and notice it writes times 10, and then you put in a 3, and that's how you'd write 2.3 times 10 to the third. And that's how your calculator would write it too. Oops. Okay. Where'd my other TI go? I had one more. No, there it is. Okay. Here's another Texas Instrument calculator. And see how above the 7, it says EE, but no, that's a shifted button. So in order to use this, you have to push the blue second and then the EE. Okay. So that's what the button stands for. So in order to get it in your calculator, if I wanted to get that number in my calculator, I'd push 4.5, and then I'd push that magic button, and then it depends on which calculator. Sometimes you got to push the plus or minus after, sometimes you got to push the change sign before, but somehow you have to get that -4 in there. So that's the order I would push the buttons. So if I wanted to put in 4.5 times 10 to the -4th on this calculator, I type 4.5. Oops, it went off on me. I type 4.5. That's what the calculator says. Then I'd push the magic button. On this one, I got to push Shift and then the E, and it just writes the letter E. And then on this calculator, I have to push -4. And on my Texas Instrument, sorry about the glare and the scratch screen, okay, that's how my calculator would write it. That's 4.5 times 10 to the -4th. And you get 0.00045. So we did these problems before. Now let's do them on a calculator. It's the same ones. Where's my stupid zoom controls? Never stay where they're supposed to. Okay. Oops, unzoom that. So, let's see if we can be successful pushing these in our calculators. Got a calculator handy? Try pushing these buttons and see if you get the same answer this time that I got when I did them longhand. So on my first one, I'm going to push 6.0 times 10 to the 3rd times 3.8 times 10 to the 2nd. My calculator screen fills up with numbers. Okay. Okay. And it gives me the 2,228,000. That's from 2,280,000. Two sig figs, 3 sig figs. So I round the 2 into a 3 and I get 2,300,000, just like I always would. If you have difficulty using your calculator, I'll be at the Chem Tutor tomorrow morning before school. If you're gonna ask me about your calculator, I'm gonna need to be able to see it. So if you can take a picture of it, so then I could help you with it. Okay, let's try the second one. 6.08 times 10 to the 3rd minus 3.2 times 10 to the to the 2nd. My calculator gives me 5,760. It gave me the right number, but I can't do sig figs. Because I don't know how those numbers lined up. So even though your calculator will do the math here It'll always get you the right answer. Okay? It won't tell you where to round. And that's not a problem with multiplication and division. It's a problem if it's adding and subtracting. Adding and subtracting, you have to do longhand. Okay? Okay, so that's some of the stuff you'll practice on Sigfig Practice 3 today. I was going to have you practice some more, but we got waylaid by Canvas issues, so I'm going to have to press on to keep you in the same spot I need you to be. Okay. So sigfigs are about how much you can trust your data, how much you can trust your measurements, how good your measurements are. Well, scientists, when they talk to each other, they need to describe how good their measurements were. And they use two different words to describe their measurements. And the problem is, these words have been taken over by other people. And in other places, they're used interchangeably. But they mean different things in a science class. They're different from each other in a science class. Okay? The two words are accurate and precise. You think about those two, accurate and precise, those are pretty much synonyms, aren't they? Well, not quite. Here's why. Accuracy. If something is accurate, you got the right measurement. You got it right. So accurate is how close it is to the right answer. Scientists want accuracy. They want to measure what the world really is. So if the number is accurate, that means you got it right. The second word they use is precision or precise. And precision or precise is about how well that measurement can be repeated. Okay? How close together those measurements are. Because there's only one way to know if you can repeat it, and that's to repeat it. Okay? So precision is how repeatable it is. And that's what sigfigs is about. Sigfigs is about how, if somebody else was going to measure it, how repeatable would it be? Which numbers would they repeat? They would repeat all the numbers in front and then one at the end they weren't sure of. And the ones they weren't sure of would be close together. Significant figures are about precision. Are you going to be able to repeat that measurement? How well are you going to be able to report that answer? Okay. To show you the difference, how that's different than accuracy, your book did it with darts, because every textbook I've ever seen has done it with darts, but most people don't play darts. Okay, not familiar with darts, don't realize the goal of darts is not to hit the double bullseye. The goal of darts most often is to hit the triple 20. But, so I'm going to use a golf analogy. Okay, so look at golf and talk about accuracy and precision. So I go to the first hole, and my first shot goes here. I didn't like it, so I shoot again. It goes there. Take my third shot. It goes there. Okay, on a golf course, the obvious place you want to hit is the hole. Were those shots accurate? Were they accurate? Well, are they close to the right answer?
Inconceivable!
I don't think so. Are they precise? Well, they're all pretty close together. So that would be precise. So I got it wrong every time, but I got it wrong in exactly the same place. They made the same mistake every time. Okay. How could this happen? Well, it happens every time I hand out rulers for the first time. Some people are going to make precise measurements that are inaccurate with as simple as a ruler. Because on a ruler, 0 is not always at the end of the ruler. Sometimes 0 is a little ways in. And the rulers I give out are like that. That they don't put 0 at the end of the ruler. That there's a little space there. The reason why they do that is if you drop the ruler, the end moves around. If it gets bent, dented, the 0 kind of gets lost. By painting the line, it would have to be dented that far before you'd mess up where your 0 was at. That's why they don't put 0 at the end. Makes it a little harder to use, but that's why they do it. Okay? But if I handed you this ruler, lots of people would measure from the end, and they would get the same answer every time, but it would be off by this much every time. So the fact that we can repeat a measurement tends to make us believe it, but we got to watch out for the fact that we did the same thing wrong every time. Okay? So accuracy and precision are not the same. This is not accurate, it didn't go near the hole, but it is precise, they're close together. Second hole. First shot here, second shot there, third shot there. Was I accurate? Okay. Well, each one of the shots is pretty accurate, but think about where did the average shot go? The average would have been right in the middle of all those, right about there. Notice how the average is better than any of the individual shots. So it was accurate. Was it precise? Are those shots pretty close together? Yeah, they are.
Yes.
So this is what we want in measurements. We want them to be accurate, we want the right answer, and we want them to be repeatable. We want them accurate and precise. Okay. Then this hole. First shot goes here. First shot goes here. Second shot goes there. Third shot goes there. Were those shots precise? Nah.
Inconceivable.
Were they accurate?
Alrighty then.
Okay, well, what do you mean maybe? What do you mean maybe? Well, think about where the middle of this is. Where the average shot is. The average is better than any of the individual shots. The average shot is better than any of the individual shots. But would you trust it? Because I would tell you that when I make shots like this, I say, well, at least I got the hole surrounded. Okay? Am I going to be a professional golfer if my average shot is close? Nah. So just like you wouldn't trust yourself to make money golfing this way, scientists wouldn't trust data where they had wide variations and the average was close to what they expected. Still not good data. And go to the next hole. And it goes in. I'm not going to press my luck. Was that accurate? Was that an accurate shot? Well, yeah, it went right in the hole. Was it precise?
Have we learned our lesson?
We can't say whether it's precise or not. Why not? Well, precision is about repeatability. Did I try to repeat it? If I've only done it once, I can't talk about precision. Not that it has good precision, not that it has bad precision. It doesn't have precision. Okay? We didn't try to repeat it, so we can't comment on if it's repeatable. Okay, so we're not going to talk about golf again this year probably, because this is not about golf, it's about measurements. So 3 students measure the room. First one measures it to be 10.2 meters across. The second one measures it to be 10.3 meters across. The third one measures it to be 10.4 meters across. Were they precise? Well, those 3 numbers are only different by 0.1 out of 10. So that's less. That's about one. That's less than 1%. So they're less than 1% apart. They're pretty close together. So were they precise? Yes, they were precise. Were they accurate? Notice I didn't say were they accurate, yes or no, because this is not, the answer is not yes, and the answer is not no. The answer is we don't know. Because how far is it across the room? Do you know? I don't. Okay. So we can't tell if they were accurate. Now, if somebody asked me with those 3 numbers to guess how far it was across the room, I'd guess 10.3. I'd pick the middle of those. And I trust it pretty good as long as I trusted the meter stick and the students doing the measurement. Okay? So you cannot have precision if you don't repeat it. You can't talk about accuracy if you don't know what the right answer is. Okay, so accuracy can be true of an individual measurement. The ball went in the hole. Or if I have several measurements, I want to talk about the average of those measurements. So I add them all together and divide by how many there are. Arithmetic mean. So if I got one, I can talk about it being accurate or not. If I have several, I talk about whether the average is accurate. Precision, I can't talk about precision until I've done it several times. So, how could you turn that into a question? Well, here's the kind of questions I think about. How I can turn something into multiple choice that makes you think pretty hard. I use a graduated cylinder to measure volume of a liquid. I measure 3 times. My 3 measurements are 15.6 milliliters, 15.5 milliliters, and 15.6 milliliters. I can say with confidence one of these, but only one of them. Because I got precise or imprecise. I got accurate or inaccurate. I got precise and accurate, or I got imprecise and inaccurate. So when you see this kind of problem, you have to do precise and accurate separately from each other. So first, precise. If I look at those 3 numbers, are those 3 numbers close together? Why? Yes, they are. So I can say with confidence, because that they're off by, well, 2 of them are the same and one's off by less than 1% again, 0.1 out of 15. So it is repeatable. It is precise. So my answer is down either to precise or precise and accurate. Okay. Now I have to decide, was it accurate or not? Well, What's the volume of the liquid? Does anybody know? I don't know. If I'm making up the question, I don't know. Nobody knows. So if I don't know the original amount, I can't tell whether it was accurate or inaccurate. I've got no information about accuracy at all. All I've got is about precision. How repeatable it is. I know it's repeatable. I just don't know if it's right. Now, I'm going to tend to believe that it's about 15.6 milliliters. I'm going to trust myself. Okay. Now, all four combinations are possible. You can be precise and accurate. You're able to get the right answer and you're able to get it every time. That's what we hope for. You can be precise but inaccurate. That means you got the same answer, but you got it wrong every time. You did the same thing wrong every time. So that's precise and inaccurate. Okay. You can be inaccurate and imprecise. That means your answers are all over the place. It's a bunch of random numbers. And here's the tricky one. You can be accurate but not be precise. And there's a scientific term for that. No, it's not a scientific term. Just a general term. A general term for you can get the right answer, but you can't repeat it. And that term is lucky. Okay. If you get the right answer once, but you can't repeat it, you have been lucky. And science doesn't rely on luck. Okay? We don't want luck being the way we figure out stuff. Okay, so we got the numbers we're going to deal with the measurement. How are we going to get that measurement? Okay. Where'd it go? It was right here. Okay, the way you're going to get the measurement is you're going to observe stuff. And there's two types of observations, qualitative and quantitative. Qualitative tells me the qualities of it, tells me what it's like. It describes it, but it's not really a measurement. Hot. So, if somebody says the room is hot, what does that tell you about it? Well, that tells you that it's at a temperature they would consider it hot. Okay? My wife and I disagree about this one every night. Okay? She says it's too hot in here, and I said, no, it's not. Large. Try to picture in your head something that's large. Are the things in your head the same sizes as the other people are thinking? Because I was thinking of a large atom like uranium. Large gives you a way of comparing, but large by itself doesn't really describe anything. Okay? Quantitative is the other kind of description. When I see the word quantitative, I see the word quantity versus quality. Quality, what it's like. Quantity, how many. This, quantitative, is what we mean by measurement. Described with numbers and units. Okay. 100 degrees Celsius. Quantitative. A number, 100. a unit degree Celsius. 15 meters. A number, 15, a unit, meters. Those are measurements. Okay. So, see, I tried to pick ones that would substitute there. That 100 degrees Celsius would describe something that's hot, boiling water. 15 meters would describe a large bubble. Well, yeah, that'd be a big bubble, 15 meters across. Okay? Big. Which one do scientists prefer? And why? Scientists prefer quantitative. Scientists prefer measurement. Why? Well, we get to use one of our vocabulary words. It's more precise. Say, what do you mean it's more precise, more repeatable? Okay, when I lay down in bed with my wife at night and she says it's too hot in here and I say, oh, it's a little bit cool, we're going to disagree with each other. We could not repeat the same measurement, the same observation. But if my wife says, it's hot in here, and I go read the thermostat and say, it's 72, that's not hot, she would be able to get up and look at the thermometer and see it was 72. Now, we would agree that it was 72. We'd agree on the quantitative. We still may disagree on the qualitative. That still may be too hot for her. And that shows that we have preferences, biases. I remember when I first moved to California from Michigan, and it got to be about 60 degrees in the morning, and I watched my students put on heavy coats. Now, their bias was they thought that 60 was cold enough for a winter jacket. My bias was that when it finally warmed up to 60 in the springtime, I put on shorts. Is 60 degrees Fahrenheit hot or cold? Depends on where you're coming from. The real reason why we prefer quantitative is it's testable. If somebody says it's 100 degrees, there's a way to figure out if it's 100 degrees. And you're both going to be able to check it. Okay, so I'm going to try something that we haven't tried. Well, we did try it. You just didn't know we tried it because it didn't work. Okay, so let me get over here. Find my mouse. Okay, let's try this. It doesn't work. It's really bizarre. It worked last period. It doesn't work on this one. It doesn't work this one. Huh. I can't do it here. Zoom. All right. We'll have to do it the hard way. So, which one is this? The rust was heavier than the iron. Is that qualitative or quantitative? Well, it doesn't have a number, so it's got to be qualitative. See how that doesn't draw the same picture in everybody's head? Okay? Because you may have been thinking about a pile of rust next to a screw. I'm thinking about a pile of rust next to a big pile of iron. in the middle of a yard. Hey. It is 354 kilometers to Vegas. Qualitative or quantitative? Well, it's pretty obvious. It's got 354, number, kilometer, unit. That's a quantity, so it's quantitative. The solution is bright green. Oops. Qualitative or quantitative? Well, here's the thing. Is the bright green in your head the same color as the bright green in my head? Exactly the same shade? Not really. We might agree it's green, but your bright green may be different than mine. So that's qualitative. And scientists prefer quantitative. So we're going to have to turn this into a number in order to use it later this year. We're going to have to turn the color of light into a number. We're going to measure it. We added 18.3 grams of calcium chloride. Which one is it? Well, it's got a number, it's got a unit, so it's quantitative. And here's the trick question. Want to tell you a good trick question? I think the car is cute. Is that qualitative or quantitative? The correct answer is, of course, C. It's an opinion. It's not an observation. Okay. If somebody walks up and says that car is cute and somebody else says that car is not cute, who's wrong? Well, beauty is in the eye of the beholder. Neither one's wrong. But if somebody walks up and says that car is blue and someone else says no, it's yellow, somebody's wrong. It's either blue or it's yellow. It can't be both. So that's see the difference between a fact and an opinion. Okay? So scientists want to not have opinions. They want quantitative facts if they can have them. Okay? So scientists prefer quantitative. And we've already talked about that in sigfigs. Sigfigs are quantitative. Sigfigs are about how much you have. So sigfigs are about precision. Sigfigs is how repeatable is it? But accurate. How close is good enough to be accurate? Well, if we want to talk about accuracy, right, we need to attach a number to it. And the number we're going to attach is error. Error is a scientific term that is how wrong you were. So you take the accepted value, the right answer, based on reliable references. You looked it up in the book. And you got an experimental value, something you measured. So you looked up something, and you measured something. How are you going to figure out how wrong you were? Subtract. Right? Just subtract those two. So I take my experimental value and subtract my accepted value. Now, if my experimental value was 5.0 and my accepted value was 4.8, I get a value of 0.2. And that tells me I was wrong by 0.2 and that I was too big. Because this can be a negative number. What if I took my 5.0 and subtracted 6.8? Then I get negative 1.8. And a negative error tells me that my value was too small by 1.8. A positive one tells me my error was too big by how big you were, by 0.2. Now, if I'm off by 75 meters, am I a long ways off? Well, it depends on what I'm measuring. If I'm measuring how far it is across a football field, being off by 75 meters would be pretty awful. But if I'm measuring from here to the moon, being off by 75 meters wouldn't be that bad. So error doesn't tell us a lot. What we really need is percent error. So we take the error, the number on top is just error, the error we just defined, how wrong you were, and divide it by the right answer. And the bigger the percent error, the more wrong I was, the worse it was. So I turned accuracy, how wrong I was, into a number, how wrong I was. I took something qualitative and turned it into quantitative. Notice this has subtraction, multiplication, and division in it. So this is why I had to talk about complex sigfigs. So scientists are always going to try to take something qualitative and turn it into something quantitative, because then they can learn more about it. Okay? Sorry I talked long and fast. I had planned breaks in there, but Canvas got in our way today. I apologize for that. Practice 3's up there, and there'll be another short one for tomorrow, and then I'll see you again on Thursday. Sorry about taking so long, talking so much, but Canvas got in our way today. All right, have a good one. I will see you later. Enjoy your lunch.
I have a question.
Sure. What can I do for you?
Will the notes be up on Canvas?
I will get them up on Canvas the best I can. I've been recording it to matter, but the poll doesn't work. That tells me the recording didn't work. If not, I can give you notes, the same notes equivalent from last year.
Yeah, because we kind of missed a lot at the beginning.
Okay, I'll try to get those up for you. I know I recorded last period, so I might just have to tweak it a little bit.
Okay, thank you.
Yep, I try to help. If you got questions, ask away.
I'm good. All right.
Okay, take care.